All right, we are back. This is Chapter 8, Basic Statistics. We're on page 12 of the note packet. We're looking at 8.4, hypothesis testing for z-test for a proportion. And so we're back to proportions. That is like the probability of something occurring. So between a one and a two-tailed test, it's all exactly the same. It's just how you find z is going to be different. And so that's why I've had a lot of students think that this was one of the easier tests. There's a lot of writing though. That's the downside, but there's not a lot of math in this one. And they're very, very, very similar problems. So on this one, when we find our z-score, we're going to use p hat minus p over the square root of pq divided by n. That's how you find z. But everything else is going to be the exact same as what we just did. So here, let's take a look at an example. It'll make a little more sense. So page 13. I wish to show that the majority of American voters support the nationalized health care. In a random sample of 300 American voters, 142 supported the AHCA. All right, so test the claim at a 5% significance level. All right, so again, with this particular claim, state the hypothesis is always the first thing, the null and the alternative. So we're gonna say, I'm gonna say the null is p equals 0.5 and the alternative is p is greater than 0.5. You could have a different null. You could have the null listed as p is less than or equal to 0.5, and then the alternative is p is greater than 0.5. So this would be an acceptable, either one of those are okay. Again, I'm usually demonstrating it with equals 0.5 because that's what your book is doing. That's how most of the problems in the book and how the problems on the test are going to be. In this context of this problem, this probably makes a little more sense because then it's less than or equal to 0.5. You know, less people are for the American Health Care Act, or more people, more than 50% are. So that one, in the context of this problem, that might make a little more sense. I'm probably still just going to put that though. So here we are. We get to use z again. Remember proportions, you get to use z-scores. So we're not using t anymore. We don't care about the 300 people. We're going to go all the way down to the bottom on the chart. So let's find our critical value. They want 5% significance level. So that's that shaded area, the critical value. You look it up on your chart. That's 1.645. You look up one tail, 5%, and then you follow it all the way down to the bottom, and that's the 1.645. All right. Okay, so now let's find our test statistic. So z is equal to, well, p hat we gotta find. So p hat is gonna be 142 over 300. Ooh, that evidence is not looking good for greater than. It says they want us to test is it greater than, and our average was less than 50%. So it's going to end up in this side. I can tell you right now, we're going to fail to reject. But let's continue. So p hat we need for the formula. What else we need is p, which is right there, 0.5. That's also why I like to stick with this. It makes a little more sense when you're labeling things for the actual work. And then q, not q hat, q. So we're 1 minus 0.5. So you've got to be careful. This is a distinction that a lot of people mess up. Later in the next sections of this chapter, we're going to do confidence intervals. And then we're going to use p hat and q hat. This one we're using p and q divided by n. and then taking the square root. And then p hat falls in right there. We don't use q hat. It's not in our formula at all. All right? Okay, so let's calculate, what was n was 300 people. So here goes. We got 0.4733 minus 0.5 divided by the square root of 0.5 times 0.5 divided by 300. So you do 0.5 times 0.5 divided by 300, do that all in your calculator, and then take the square root of that number. So here, I'll show my work. So that's a really tiny number, 0.000833. And here, let me give you a quick explanation. 7 negative 0.02886, almost 1 standard deviation below the mean. Negative 0.924. So again, we take that z-score of negative 924, and we graph it. If it falls into the shaded area, we reject the null. If it falls into the unshaded area, we fail to reject the null. This is well into the unshaded area. So we fail to reject the null hypothesis. Our conclusion is it's equal to 50% or it's less than 50%, or we say there's not enough evidence to say it's more than 50%. That's for sure. All right, so letter D is on the 5-step process, not letter D on letter D here. So what was letter D? We make our conclusion, fail to reject null at 5% level, 5% significance level. Okay, and now letter E in the context of the problem. There is not enough evidence. There is not enough evidence to conclude the majority of voters support, and I'm going to use the abbreviation they have there, AHCA. All right? So now it says, let's find the p-value. For this, you can find the p-value. So the p-value on this one, we look up. Now, we want this part, though. We want this shaded area. So it's from here above. So we're going from there above because of the greater than sign. It was a one-tailed test, but our test statistic ended up in the negative realm, so it's greater than 50%. So when you look that up on the chart, when you look up negative 0.92, here, I'll show you the chart. So here's our chart, negative 0.92, 0.1788. All right? But this shaded area is clearly not 17%. So this is one of those times when we have to say, all right, so here, this is a different problem. We're doing the p-value. So the p-value, we look up, z is equal to negative 0.92, and that kicks out 0.1788. That's what, from looking up on our z chart, we get, but we want 1 minus that. And so that is our p-value, is 0.8212. And so what does that mean? That means if the null hypothesis were true, if this were true, either this one or this one, equal to 50% or less than or equal to 50% were true, we would get results like this 82% of the time. So that is evidence to the null hypothesis. If it were a really little percentage, if it was like 0.3% of the time or something, then we would say reject the null and conclude the alternative that more than, because then if the null were true, we'd only get results like that 0.3% of the time. Then we would have rejected it and it would have been in the shaded area. We failed to reject because it was in the unshaded area from our critical value setting. All right? Okay. One more problem, just like that. Let's see. In order to use a z-test, we need to make sure the normal distribution approximates the binomial distribution. Should not use the test if n times p hat or n times q hat are less than 5. Yeah, that's true. Okay, and you won't have to worry about that. That's more of an advanced concept, and we're not going to throw that at you in this in basic statistics, but that is a thing. So don't worry, on the test, everything that I give you on the test, on this last test, you'll be able to work out. But the whole 5 thing, n times p hat has to be bigger than 5 or bigger, and n times q hat has to be 5 or bigger. What you're doing there is you're eliminating the extremes. So we don't want to do this kind of hypothesis testing if it were extremely small probability or a really small sample size. And so those two things get eliminated by doing that little tested against n p hat times n is 5 or greater and q hat times n is 5 or greater. All right, so let's take a look at this last example. An attorney claims that more than 25% of all lawyers advertise. Okay, so here we are. The null hypothesis, again, I'm going with equals. And then the alternative hypothesis, he's saying it's more than. So greater than. All right, let's draw ourselves a pretty picture. Shade the critical value. It's a one-tailed test. It's greater than, it's just a one-tailed test. Critical value, what do they want, 5%? 5% on Z is 1.645. We probably are starting to get these memorized, right? The 1.645 and the 1.960. Okay, so now C. Oh, we got to do a little work. P hat is equal to 63 divided by 200. That's 0.315. On the notes, I calculated Q hat, but you don't need it. You don't need it for this problem. You would need that if we were doing a confidence interval, but we're not. So P is equal to point. Oh wait, these are P's, not U's. Oh no. Okay, I have P's on my notes. Now I have P's on the board. It's probabilities. I went, I don't know, my brain was in mean land for some reason. All right, so P was equal to 0.25, and that means Q is equal to 1 minus 0.25, or 0.75. So we need P and Q to do our Z value is P hat minus P over the square root of PQ divided by N. And so P hat, N was 200. P hat 0.315 minus 0.25 divided by square root 0.25 times 0.75 divided by 200. So again, do that. 0.25 divided by 0.75 divided by 200. You get this really tiny number, 0.000, how many zeros? 3 zeros, 9375. And on the top, we get 0.065. Ooh, really quick, really quick. Let me show you on the calculator because people mess this up. Oh no, don't do this. So look, on my calculator, if I take 0.25 times 0.75 divided by 200, oh, this one just reads it out nicely. Let me do a more extreme one. Let's go 0.25 times 0.75 divided by 1,000. Let's pretend we had 1,000. Nope, that isn't going to do it either. 0.25 times 0.75 divided by 100,000. Okay, I went a little extreme there. Sometimes your calculator will kick it out in scientific notation, and that throws people off. Let's go divided by like 100, 1, 2, 3,000. I can't believe I can't get it to go into scientific notation. 0.25 times 0.75 divided by 1 million. 1, 2, 3, 4, 5, 6. By 100 million. There. So look, it's really hard to see. 1.875, and then it's got a little negative 11. That means point and then 10 zeros and then 1.875. So be careful, because some of your calculators will automatically kick it into scientific notation, and students accidentally put 9.3 down there. So don't do that. All right? Okay. Sorry it took so long for me to get it into scientific notation. All right, so now we continue that row here. 6.5 divided by, when I take the square root of that number, it's not as little, 0.030619. And then when I divide, I get 2.122. So 2 standard deviations above the mean, 2.12, is right here. So our z-score is 2.122. Shaded area. Remember, shaded area means reject the null. So we reject the null. Hypothesis at the 5% significance level. And so then let's do our write-up. That was our conclusion, reject the null. Our write-up then would be, there is evidence to conclude over 25% of lawyers advertise. There is evidence to conclude that 25%, that over 25%, sorry, over 25%. Over 25% of lawyers advertise. All right. And that's it. The next one will be 85. So, just real quick rundown on that. Lots of people make this mistake. They say, okay, I did this sample of 200, a simple random sample of 200. I found 63, did advertise. That's 31.5%. 31.5% is more than 25, so I can just make that conclusion. I can just say, yeah, 31 is bigger than 25, so P is greater than 25. You can't do that. We have to take into account the standard deviation to see if that's significant or not. If it, is it significant at the 5% level or the 1% level or the 0.5% level? So those significance levels are set before you run these experiments, but you've got to be careful, because you could say, like, oh, what if it turned out where the p-value ended up at 7%? Well, a lot of people say, well, that's not very likely. 7% is small. But if you have it set at 5%, we would fail to reject, and we'd say, no, it's not significantly different at the 5% level. It is different, but it's not significantly different. All right? And so that's what we're talking about with all of this hypothesis testing. The upside of these problems are they always follow this same pattern. The hypothesis, draw the pretty picture, figure out the test statistic, make your conclusion, write it up for normal people. All right? All right. We'll see you on the next one.